This is question 1 on the 2026 AP Physics 2 exam on the free response section. So looking through question 1, we have a sample of n moles of an ideal gas in a large sealed container with a fixed volume, and then a small sphere of mass m sub s is in the container, and the volume of the sphere is much less than the volume of the container. So initially, the gas is in a state with pressure P and volume V, and then the sphere is in thermal equilibrium. The gas undergoes a heating process since it has a thermally conducting container, and then it's going to be in a new state with a triple pressure, 3P. And then again, the sphere is still in thermal equilibrium with the gas. And since it is a fixed volume, it should be at a higher temperature. So part A, I, the graph in figure 2 represents the number of atoms per unit speed as a function of atom speed for the gas when it's in state X. So since we are tripling the pressure through this heating process, keeping the volume fixed, increasing the temperature of the gas, we should have the average speed increase, as well as having the distribution of the atoms sort of spread out a little bit more. So I would imagine the graph for state Y at the higher temperature should look something like this, where the distribution is a little bit wider. The average speed is a little bit faster since it's the higher kinetic energy on average for each gas atom. And then you should have a little bit more of a distribution on the spread. So, all right, on to the next part. Part double I, derive an expression for the change delta T in temperature of the gas for the heating process as it goes from state X to state Y. State Y was at 3P and state X was at P with a fixed volume. Express your answer in terms of N, PV, and physical constants. Okay, not too bad. So this looks like it's going to be the ideal gas law equation. So we'll start with that. So we'll say PV equals nRT. So in state X, we have PV is equal to nR times the temperature in X. So the temperature in X should be PV over nR. And then in state Y, we had 3P V is equal to nR times Ty, so that the temperature at state Y is 3PV over nR. And so then to find the change in temperature, that should be the final minus the initial. So Ty minus Tx, which should be 3PV over nR minus PV over nR. And if you simplify that, that should be 3PV over nR. That should be it for the expression for delta T. Okay, on part triple I, derive an expression for the specific heat Cs of the sphere. Express your answer in terms of N, M sub s, PV, and Q sub s. Where Q sub s, I believe, was the thermal energy transferred to the sphere. Let's go back and look really quick. So the total energy transferred to the sphere during the heating process is Q sub s. Perfect, okay. So if we think about this, in that heating process, we're gonna have the change in temperature really be this expression. So we could say Q is equal to mc delta T, pulling that from the equation sheet. So the energy transferred to the sphere during the heating process should equal the mass of the sphere times the specific heat of the sphere times the change in temperature of the sphere. And the magnitude of the change in temperature of the sphere should match the magnitude of the change in temperature of the gas. So it should be 2PV over nR, since the gas increased by that same amount of temperature. So we'll plug that in here. So we'll say Q sub s is equal to M sub s times the specific heat times that temperature change, which is 2PV over nR. So therefore, the specific heat expression should be Q sub s, M sub s divided by 2PV over nR. And that should be it. Now for part B, This looks like a separate experiment. We have an insulated container filled with a liquid of mass ml and specific heat Cl, and the original sphere is submerged in the liquid, which has a mass of ms, where ms is less than ml, and the specific heat is also less than the specific heat of the liquid. The initial temperature of the sphere is greater than the temperature of the liquid, so it sounds like the sphere is going to cool, transfer thermal energy into the liquid. Later, the liquid and the sphere reach a thermal equilibrium, and the absolute values of the changes in temperatures are delta T sub L and delta T sub S respectively. Indicate whether delta T sub S is greater than, less than, or equal to delta T sub L. Okay, so it seems like if you think about this for part B, you can draw out a sort of a scenario like this. We're going to have the sphere and then the liquid, each with their specific masses and specific respective specific heats. The change in temperature, or the thermal energy transfer to the sphere, should match in magnitude the thermal energy transfer to the liquid. And so it seems like energy is going to go from the sphere into the liquid. So the cooling amount of the sphere should match the heating amount of the liquid due to conservation of energy. And so if we think about this, how this is going to work, the mass of the sphere times the specific heat of the sphere times the change in temperature of the sphere, which should be negative since it's going to get colder, should equal the mass of the liquid times the specific heat of the liquid times the change in temperature of the liquid, which should be positive since it's going to be getting warmer. Now, they did tell us that the mass of the sphere is less than the mass of the liquid, and the specific heat of the sphere is also less than the specific heat of the liquid. Let me double check that really quick. Yep. So given that, that must mean that the magnitude of the change in temperature of the sphere must be significantly larger for this to actually equal, for the thermal energy transfer to the sphere magnitude to match the magnitude of the thermal energy transfer to the liquid. So that should be our answer here. So we can say, because both the mass of the sphere and the specific heat of the sphere are less than that of the liquid, and specific heat of the liquid, respectively. The change in temperature of the sphere must be a lot larger. We'll just say it in symbol form. A lower mass and specific heat means the temperature change must be greater for the same energy transfer. So both a lower mass and lower specific heat allow the sphere to have a larger change in temperature. For the same amount of energy transfer. And I think that's